A lot of times I would look at formulas just to make sure I'm writing. Like, we're about to talk about the homework one day, make sure it's plus, and it is plus, you know, but yeah.
What I did look at is like going from PKA to KA, make sure.
Yeah. So, on this homework, I extended the availability. It's still open right now until tonight. The homework that was due last night, because a lot of people were asking about question 5 specifically, but let me do a little bit on 4 first. What is 4 asking you to do? Okay, delta G, well, of both sides, but then delta G of the reactant. So the products minus the reactants, right? To get the total delta G, and then do what? Identify as either spontaneous or non-spontaneous. How? If it's positive delta G, it's non-spontaneous. Negative delta G, it is in fact spontaneous. Okay. Now, technically, since we're at standard free energy here that it's asking about, and standard condition is 25C, we'll call that delta G naught, right? That we're calculating there. So number 5 is going to ask for the next step then, delta G, so that you can use it to calculate the equilibrium constant. And I think this is where people have some difficulties. So what's our governing equation here for this? Now, I don't want products minus reactants, so we're going to need that, but that's the delta G naught. I need delta G, and there's no superscript 0 in this guy. So what's my equation for this? Okay, let me put that, hold on a second. You do, in fact, the delta G naught that you would have calculated in number 4, right? And then what else?
Plus
RT LN Q, right? But, okay, I'm gonna put Q first. Then, so that's at any ratio of products to reactants, right? But this question wants what? Equilibrium constant. So where's that gonna go? Where the Q is. All right, so now I'm going to make it K, right? Instead of Q. That's just Q when we reach equilibrium. This going to change? No, because this is the part that you look up in a book, right? In a table, the table G, right? So our delta G naught is our delta G naught for that reaction always, okay? But this is important. When Q becomes K, what happens to delta G? It's 0, right? Because if it were positive, then it would be non-spontaneous. If it were negative, it would be spontaneous. The only thing in between is for this to become 0, right? Okay, so then we need to, let's see, let's take this A here. How am I going to do delta G naught for this right here? What would you do? Ignore the temperature for right now because we're doing delta G naught. Okay, that doesn't matter yet. Go in a minute. What would you do? Let me go to the table and do what on the table?
On the
Okay, so here you are. Second column here is delta G. So delta G naught of F2O seems to be positive 41.9 kilojoules per mole. For F2, look here. Line 0. Because it's a gas that is a gas that's standing, that we define that as a 0 state. What do you think the oxygen gas is going to be? Also 0. Does that make sense? So my delta G naught here is 2 because my reaction had 2 in it, right? The coefficient coefficient here was 2. So 2 times this minus 2 times 0 minus 0. So just 2 times this. Okay? Does that make sense? So positive 83.9, check me on that. 83.8 kilojoules per mole. Somebody check that with that. It's 83 positive. Is it 83.8? Yeah. All right, cool. So that's going to be, so not equals positive 83.8 kilojoules per mole. All right, cool. Now, the question wanted us to do what? Now, a lot of folks were saying they didn't understand how to do this, right? What's going on? Tell me what the difficulty in trying to do this is. It's, I don't know, it might be. What, talk me through it. What would you do here? All right, cool. All right, Alexis, what would you do first?
Divide by.
I see that, but I would like to do it next, not first. Okay? Try to remember an idea of when you're moving stuff around algebraically. I'm not going to guarantee you this is a hard and fast rule, but generally you kind of want to go opposite from your order of operations.
So you minus the.
Yeah, I agree with that. So we'll subtract delta G naught from both sides. We get negative delta G naught, 0 minus this is just this, equals, now we have your RT ln K. Now we can do your divide, okay? All right, so now we are at negative delta G naught over RT equals ln K. How do you unnatural log? All right, so I'm going to take E and raise it to this, and E and raise it to this. And this part cancels out, leaving the K. Right? And we calculated the delta G up there, right? So now we can just say, well, all right, then E raised to the, so it's, remember this is negative delta G, okay? So it's the opposite of whatever you calculate. In this case, you calculated a positive, so now this piece makes it be a negative. So negative 83.8 kilojoules per mole over, what am I going to use for my R here?
0.
Okay, so interesting the way you said that. You said 0.008314. Right? I think of it as 8.314, but be careful with that because that's in joules. He's already converted it to kilojoules. Does that make sense? So kilojoules per mole. Okay. Kilojoules, I think mole. Okay, right?
Yeah.
Okay. And then we need to multiply by, well, units here says I need to multiply by what? Kelvin. Good. What do I have? Celsius. So really don't get tripped up by that. So 373.15 K. Okay. Now look, I don't know how to convince y'all, but do each piece of this and write it down. If you run out of pencil, tell me and I'll give you another. Okay, just write them down, please. I don't know why, but folks just don't like writing all the steps. I just don't know why. Because you lose points. Now, E to the negative 83.8 kilojoules per mole over, this times this, somebody, please. Agreed?
3.102.
3.102, what units? Let's see. Joules per mole. And remember, that's a good check for you. If your units do not cancel out and you're about to race into a power, be worried. Be very, very worried. Okay? So now we have e to the, what's that over that? Say it again. Maybe 27 sounded right. Maybe 27, not something. Okay. All right, now make sure you can raise e to that on your calculator, please. It's not working. What's not working? From it. Looks like it's working. You just did it all at once. You've just done the next step. What'd you get? What was it?
0.85. Times 10.
That's your check. Okay? So this claims that for this reaction right here, at 100C, it's almost all reactants. Okay? 10 to the negative 12 products. That makes sense? As you increase the temperature, all right, you're going to get smaller value up top, so you'll get a little closer to e to the 0. So this one would be very temperature dependent, and you could increase your products by heating your reaction. Okay. All right. Y'all gotta talk to me. Y'all gotta tell me why that's cryptic. Why was that difficult? I'm really asking. That's not rhetorical. I'm really asking. Like what makes it hard to access that question? Okay, fair. Well, what PhD are you not used to on? Having to deal with the laws?
Just not having, I haven't done thermal chemistry.
Okay. Some people never done it, so, you know. No, I'm really asking because I don't know what makes it difficult here. Got an idea?
I'm not used to the double G.
Okay.
I throw that in the mix, I was like,
Okay.
that's in my head, I'm gonna have to do a K equals a auxiliary reactor.
Oh, right, because you're doing K the other way. It's the same K. It's just that this would be a way. So you got to remember that all these things are interrelated, right? And so sometimes we would calculate K from a delta G value, or also a lot of times what happens is you set the reaction up, measure the equilibrium values, and back calculate the delta G. Making sense? So that's just algebraic fluency, being able to manipulate those reactions around. That might be the difficulty of the algebraic fluency. I don't know. Other thoughts? Shall we go on to redox chemistry? Okay, that homework is open until midnight. It should have closed 15 minutes ago, but they extended it. Noticing on the last one, Mark, that a lot fewer folks did their homework, but you did yours, and I'm wondering if there's like an inverse, if it has to be, I don't know. All right, anybody get the joke? Good. Anybody else get the joke? Talk to me. Tell me about it. I know it's terrible to spoil a joke, but tell me anyway. Iron oxide is called rust is true. What is this idea of oxidation? From Chem1, what was it? Oxidation. Next shift class, did y'all do an acronym for it, maybe? Oil rig? I don't like the acronyms. Kara's looking at us like, what the hell, oil rig? What is that about? Right? I don't do the acronyms. I'll say the way I remember it. Did you? You do not remember? Okay, all right then. Maybe he doesn't either. I don't know. Oh, as a reminder, no lab today. Remember that. Okay, we are done with that. I don't know if I did. Let me check. Yes, we are in. Thank you. Okay, a little bit of physics. What is the idea of electrical potential? What is that? What is that concept? What is electrical potential? How could you, what is electrical potential? Okay. How about, where do y'all encounter in like high school the idea of potential energy? What usually gravitational potential energy? That's what usually what it is, like the ball has more potential energy on top of the hill, gains kinetic energy on that normal, everybody access that. Okay, works the same with electricity, okay? Potential energy is your driving force, the buildup of potential that's going to cause a doing. And the doing is the same thing, electrical current, okay? That's kind of analogous to our kinetic energy. Okay, well, using that idea then, how would we typically measure electrical potential? Yes. All right, now if I ask it that way, does that make it a little more accessible? Y'all have the idea of voltage? What is voltage? What's voltage? You do not know. Say again. Well, be careful, and I'm trying to get you to use these terms separate. Voltage is not current. Voltage is that potential. Okay? You might know how you measure current, electrical current. That's energy. Good. That is good though. Amps. Ohms is resistance to amps. Okay? So, all right. So now we've got our units that we're going to talk about, volts and amps. Okay? So if let's say I put 2, 4, 8 AA batteries. Okay, 8 AA batteries. So you're picturing 8 AA batteries in a bundle, right? What if you touch both sides with a piece of metal? AA batteries. Touch the positive and the negative ends at the same time with a piece of metal. AA batteries. I got a bundle of 8 of them for a reason. I'll tell you what that reason is in a minute. Right. Yeah. So what's going to happen to your wire? It might heat up a little bit, right? Okay. I have 8 of them because if you put 8 of them together like that, you make 12 volts. Okay. Let's take that same piece of wire, pop your hood on your car, and cross the positive and negative terminals. Please don't do this. It's not a good idea. Why? It will be dramatic. What's going to happen? Yeah, you're going to burn that wire. Now wait a minute. Hold it. Your car is also 12 volts. Why would 12 volts do this in one circumstance and not the other? Yes, the car battery is set up to provide a hell of a lot of current, a lot of amps. Okay, so electricity flows in both cases, and the potential is the same. All right, does that make sense? All right, let me give you another example. I don't know, so danger here is that I am a geologist and I tend to think of things a lot of times in geology senses. So I don't know how much sense this is going to make, but I'm going to try it anyway. We have 4 scenarios. Okay? Scenario 1 is really high cliff. And scenario 2 is an equally high cliff. Okay? Scenario 3 is a little drop. It's kind of cliff-ish, but it's not all that high. Scenario 4 is the same thing. Okay? And in scenario 1, got this little trickle of water coming over the cliff. Okay? Makes sense? And it's going to splash down here. Right? And in scenario 2, you got this huge amount of river coming over. Right? It's going to come down, splash down here. Okay? Make sense? So far you follow me? All right, here, I've got a little trickle of water. Here, okay. So what I'm trying to illustrate here is the differences in voltage and amperage. Voltage potential, electrical potential is analogous to the drop. Do you see that the potential energy drop is the same for each of these? Yes? The flow is not, right? You know, this is it'll trick, okay. This is like, wow, right? So there's a lot of flow here, and there's a lot of flow here, right? So amounts of flow is analogous to current, and amount of topography drop, elevation drop, is analogous to voltage. Does that make any sense? Maybe. Okay, we'll try. And then conductor and insulator. Find something, you mentioned ohms, right? That's how we measure resistance. So a high ohm value, a lot of resistance. Why do some things resist? So, I had a girlfriend once and yelled, oh my gosh, yelled at her kid, right? So why are you yelling at my kid? I'm like, to get him to drop that fork that he was about to put in the house. Right? So what would have happened if you put a fork in an outlet? Yeah, not good things, right? But all the time you grab a cord and you shove it right in the outlet. Same exact method the kid was about, right? It's the same motion. Why was that okay? Because it's insulated. Well, why? What is that property? Insulation. What happens? Do you know the molecular reason? Yeah, you know, highest occupied molecular orbital versus lowest unoccupied. But yes, it's the jump, it's the delta. Good. Yes.
Another way of explaining voltage. It's actually
What's actually happening with voltage? So
on the electron.
no. More availability, more potential energy difference between the two. Let me think how else. So my waterfall analogy is that the height of the waterfall is higher. It's not about how much water is flowing over, it's about how high. If you measure the elevation of the top and the elevation of the bottom, the difference is.
So you're saying that voltage would be the difference in availability, you mean like positive and negative?
Not just the availability, we're gonna relate it back to delta G, right? So it has to do with the thermodynamics of the system, right? Okay, so let me think of that side of it. If I give you a value of -2 kilojoules per mole, is that spontaneous? Yes. What if I say, okay, well, it's -2 kilojoules per mole, but this other reaction is -598 kilojoules per mole. Well, both are exothermic. I mean, both are spontaneous. Both are spontaneous, right? So it doesn't matter. Would you agree that it doesn't matter? One's a lot more, right? And so that -598 kilojoules per mole is probably like a bomb, right? And the -2 is like, maybe it'll happen. Does that make sense?
Yeah.
So that big difference in potential can also be translated into a voltage. And so you'll have a higher voltage. Ooh, okay. You'll have a higher voltage, right? Right when you take it off charge. Versus after you've been sitting playing Tetris all day. Right? Does that make sense? That's chemical difference. That is actually a chemical change in the battery. That's providing that voltage difference, that difference in spontaneity. I mean, we make this spontaneous or not spontaneous, but really we should also be talking about how spontaneous. Does that make any sense?
So it would be how far away from zero it is.
I agree with that. The delta G terms, yes.
So the higher the spontaneity,
Yep.
the higher voltage.
Yep. The more negative, yeah. Yeah, magnitude matters, yes. All right, well, now we're coming full circle, right? So in Chem 1, you start talking about, well, it's all about electrons, right? You remember me messing with Nevaeh, right? And no one's ever touched anyone because you're really just interacting with the electron. Okay, well, now we've come full circle. And we're back to ending up talking about the electrons and trying to look at the voltages of that and the flow of electrons or of ions. That is electricity. Let's see. Link to a talk about base units. Amps is a thing that you don't build from other units. It's one of our base units. And then there's volts down the bottom. Okay. Remind me again of that acronym. Somebody, Ulrich, you had, okay. So what does it mean? Okay. Y'all hear that? I don't do this. So y'all, anybody else? There's the other one. The other common one is Leo Gur or something. What is it? Y'all lying? Okay. I look at it this way. If, let's see, can I get rid of my waterfalls now? All right. So if I take I don't know what Leo's doing, I don't know what oil rigs are doing, but I know this is reduction. Because what was the oxidation state here? 3. What was the oxidation state here? 2. So it went down. It was reduced. Keep it simple. I don't know why the acronym is needed. That's reduction. The other way is oxidation. Be careful. I think it confuses you. But yeah. If the oxidation state goes down, it's reduction. If the oxidation state goes up, it's oxidation. And then go look up the acronyms if you want them. And then you can have a reducing agent, or a reductant is a thing that causes reduction. Similarly, an oxidant or an oxidizing agent is a thing that causes an oxidation. I think these things we make more complicated than they need to be by just trying to memorize them, right? And so I saw this a lot with high school teachers would try to memorize all this, try to memorize what's conjugate base and conjugate, it's an acid or base, right? And does it cause oxidation? Well, then it's an oxidant, right? Just keep it simple. Okay, now we get to the good stuff. Oxidation numbers, or oxidation state. Hopefully, you can dig this out of the recesses of your memory from Gen Chem 1. Talk to me about what oxidation number is. And the iron on the board might give you that example. What are we talking about there? Let's say, Mercy, if I put a Gen Chem 1 question up and it says iron 3+, right? How many protons are involved in iron 3+? And how would you know? Nope. How many protons total? Oh, okay, somebody else, find iron up there. 26, because we're looking at atomic number, okay? Yes, so there are 26 protons in the nucleus of iron 3+. So if there are 26 protons in the nucleus of iron 3+, how many protons are in the nucleus of iron 2+? Also 26, right? The same, because it's iron, guaranteed, right? Oh, well then what's different about it? Well, this one apparently has 23 electrons. This one has 24 electrons. And the difference is your oxidation state. Okay, does that make sense? So, if I wanted you to, Alexis, tell me how many protons and electrons are in a typical oxygen ion. Yeah. So what does she have to decide first here? Don't answer it for her, but tell her what she has to decide first. Not yet. Probably she could, but I would want to know, like, what does he mean, typical oxidation state? Right? Typical ion. What ion would you expect oxygen to make from where it is on the table?
Oh, I have no idea. So,
Close, but why did you say plus 2?
it's the second.
Yeah, but you went the wrong direction. Minus 2. Yeah. Okay, cool. All right, so now we know that it's oxygen 2 negative, right? So then, what was Miriam saying we should do? Your protons. How many protons are you going to think your oxygen has? Okay, I agree with that. Cool. How many electrons?
2 negative. 10.
See how that works, y'all? Yeah. Okay? All right, can't forget the Gen Chem 1 stuff. All right? So, unless you are going on to, probably not even in Orgo, do they even do this in Orgo? They do not. Okay. So probably only if you're going on to upper level chemistry, so maybe not even then. It matters a lot in real Orgo. You can have fraction oxidation states, but we'll try to avoid it. Okay, let's do a practice. I did not bring up some credits, so that's not live. So try to answer these questions on your own. This is a slide from my Gen Chem 1, right? So this is still review, all right? So, see what you can do with these questions. All right, actually, just one question. What is the oxidation state of the Fe?
Yeah, like if you find it, so the total charge on it is zero, right? Because I didn't run the charge. So the total charge on the whole thing is zero. Then you gotta try to find the bits. Right, and what can you hang a charge on the individual bits? Or so you see anything there that jumps out at you like, oh, you know what, I bet this element is going to have a charge of what? Any of those elements involved in this? Like this?
All right, well, okay, let's start with that. Hey, y'all, Mercy said start with SO4. Is that a thing y'all know? Is it on your polyatomic ions list? And it has a charge of what there? -2. So that's the key. So I think you can do it from that. What Mercy said, there are 5 of those sulfates, and each of them has a total -2 on it, right? So then start working from that. Please do work together. Talk it out loud if you want. Or something of that nature. Most of them are seen fractional, most of it states. Okay.
But these oxidation states are especially stuff. So you can have fractional states.
We'll try to. It is. So the stuff on the right, I put this up because it was the rules for how to assign oxidation states. And I didn't know if y'all would still remember those rules. They're good to have for your cheat sheet, though.
Carry oxide.
Yeah, peroxides, like hydrogen peroxide. Think about that. H2O2, right? Is hydrogen peroxide. So let's see, the H's have a +1. It's like the oxygens have a -1. That's weird. Well, that's why peroxides are so active. It's because it is weird. It doesn't like to stay weird. It likes to conform to the norm. And it does so great areas. Anybody get there from iron? Kelsey, did you get something?
Yes.
What'd you get?
Is it 2?
Is it 2? Y'all agree?
Yes.
All right. Owen, do you have a question to ask? Where's sodium on your chart? On your periodic? So what do you want to say about everything? Plus 2.
Oh, yeah.
Everybody. All right. Y'all happy with that? Can you do that? Because I would expect you to be able to do that, and then use that to make the next question, right? Because you have to already know how this works to be able to see where we're going sometimes for the next piece. Okay, another practice. Now, y'all that had me, you saw these before, okay? But I need to know from Dr. Shem's class what y'all did with redox balance. What did y'all do? The electron transferring stuff. Hold on a second. Let me go find it in OpenStax so we can remember where it is there. Let's see. So probably here. Ah. Do y'all remember it all? Here it is. Yeah, this piece right here. You remember this? What did y'all do? What did y'all do? This stuff right here. Please tell me. What happened in your class? You're pretty sure you did it, but you can have more crunchy. Like, what did you do?
I remember breaking it down to be separate.
Good. Two separate reactions. I'm going to call them half reactions. Good.
And I remember canceling stuff out.
Good. It's the electrons specifically that we need to cancel out. Okay? Keep going. Kelsey, is that ringing any bells?
I'm seeing you're like, oh, I see. I'm seeing something, but I can't.
Okay. Now, what did you do with anything with this? Did y'all? You did have to do half reactions? Okay, good. All right, cool. Let's go back to one of my slides here and talk to me about how would we approach this? Kelsey, if you see this on an exam, which you might well see one like this on an exam, right? So you see this one, where would you start?
Good question.
Okay. Where would you start?
I feel like positive.
Good. Okay, all right, let me go back to those rules for a second Carson was talking about. So those rules right there might help us. Let's see, we had, I'm gonna write it up here. We had what was the other one?
VR.
This? All right, cool. So positives and negatives, y'all were talking about. What, like we did on that previous one where you figured out that iron was 2+? Using these rules over there, can we figure out anything in this guy? Anything?
Yes, but the bromines
Or what?
are the same amount of bromines.
Okay, don't balance it yet. We use the electrons to balance it. All right, cool. That's true though. You're right. We'll have to deal with that. What about this charge stuff?
Bromine.
Uh-oh, y'all, let's fight it out. All right, tell me, because you're both right in different places on the problem. Talk to me. What do you say and why? Okay.
Oh, the bromine is the same.
Careful about standard set. It is in a different oxidation state. Does that make any sense? Okay, so really you're looking at the bromide on the right side, on the product side. Okay, so this one is in fact, what you're talking about, a -1 because of where it is on the table. It's a halogen, right? All right, and that now talk to me about, you said, but not over here on the reactant side, you want to call it a what here? You said, I thought you said, didn't you?
That it was 0.
Okay, yes, it is 0 there, but we need to convince everybody that. Why do I think it's 0? If we have Br2, okay, then who steals whose electrons? Which one's stronger? Bromine is stronger than bromine. Wait. Just this by itself, isolated. Which bromine is stronger? Neither. So nobody's going to steal anybody's electrons just for the bromine, okay? That's why that one's a 0. Anytime, one of our rules up there, so I think it is. In an elemental substance, I guess we could call this an elemental substance. But nothing is stealing any electrons from anybody else. Anytime you have, if you have just a block of pure iron, Fe, well, the oxidation state on the iron is 0. If you have a block of pure fluorine, stay away from it, but the oxidation state is 0. Does that make sense? If you have a block of sodium metal, right? The oxidation state is 0 until it sees water. That's spontaneous. Okay, yeah. So, does that make sense? So, pure things, bromine included, the oxidation state is. What about for gallium over here? Why? Because it's by itself, it's just pure gallium. It's the same reasoning, right? That one's also 0. Okay? All right. So, what about those little reactions? I call them half reactions that Kelsey saw before. How do we want to build those? What would you like to start with here, Owen? What would you like to start with? It can be either one you want. You want to do the VR? Let's do the VR. So, all right. So we have VR in what state here on the left? All right, I'm going to put exactly what she said. I'm going to put VR in a 0 state. Okay? So I'm talking about an atom of VR. I know it comes in twos. We'll get to that in a minute. Okay? But each of those, regardless of how many we have, is in a 0 state on the left. But on the right, y'all decided, Carson said that it should be what? Well, how did it do that? So wait a minute. Earlier, when I was asking Mercy about protons and electrons in ions, right? So let's do the same thing. Bromine here. On the left, bromine has how many protons in it? How many protons for bromine? What did you say? Okay, 35. Okay, on the left, the reactant side, how many electrons on bromine? 35, because it needs to be the same, right? Okay, good. Okay, but now on the product side, how many protons is my bromine going to have? Still 35, it's still bromine. How many electrons is my bromine going to have? 36. But I do try to laugh at it. So, well, okay, now wait a minute. Then you're saying it has 35 electrons here and 36 electrons here. And I need to write that, right? All this is just accounting, okay? There are no actual loose electrons that fall off. It's just accounting. We're just going to write it as part of an equation like this. So the bromine gains 1 electron to become the bromide. Okay? Good so far. Happiness? All right, Kelsey, let's do the next one. Now I need the gallium. What do you want me to start with? Okay, good. So it's a gallium 0 to start with. Okay, all right. Ooh, we didn't figure out we didn't figure out what it is on the product side yet. How are we gonna do that? Hint.
Look at the,
Yeah, just like we did this, right? But this was much easier.
okay. So maybe like one.
Keep thinking through. No, it's not one, but keep thinking.
I need a little minute.
Okay, how did y'all figure out how did you figure out the 2 plus here?
Um.
Look at all the other,
Right.
what else is there? Oh, no, you're just looking at the stuff in this.
Okay. So the negative one. It's there.
How many of them?
3.
Oh,
Okay. So it would be 3.
yes, ma'am. Y'all see how she got there? Okay. All right, you know what question is coming next, right?
Yep.
Yeah, Alexis,
Ready.
how many protons does the gallium on the left have? Gallium,
31.
okay. How many protons does the gallium on the right have?
34. Wait, no, 31.
Okay. But you were answering electrons, right?
Yeah.
Yeah, okay, so how many electrons here? Same as the protons. Okay, but careful, how many electrons here? Good. 20. Good. Does that make sense? It lost 3 electrons, right? Okay, so I'm gonna put this, so we had all 31 electrons, but apparently 3 of them fell off. Does that make sense? Yes? Okay, but there's a problem here. Kelsey did say that she remembered that we had to cancel, or was that Carson said we had to cancel stuff out? That was Carson? We had to cancel stuff out, but it's especially the electrons, okay? You can't have loose electrons running around in your lab, somebody will get electrocuted. Okay, so we have to account for all the electrons. If we've got 3 electrons on this side, then we gotta have precisely 3 electrons on this side. We have to account. Okay, so I'm gonna do that by multiplying the whole thing, both sides, by 3. Okay, and that 3 is based on just getting a least common multiple, actually a common multiple, I don't care if it's least or not. A common multiple between the number of electrons, so they have the same number of electrons on both sides. Sometimes you'll have to multiply both things to get an equal number of electrons. Okay? Make sense so far? Distribute. So I've got 3 PR zeros, and I've got 3 electrons, and I've got 3 PR ones. Yes? Do my electrons cancel out? Yes, then we're good. Okay, but a thing is going to come up now, it always does. And so I wanted to put a hard one in the slides to make sure to cover it now. Okay? A real hard one. So, will this 3 BRs that I have here in red, will this make us happy over here? Yes. And we have 1 gallium. Okay, cool. This problem comes up, I see a lot of folks struggle with this idea right here. We have 3 atoms of Br. Does that make sense? But they come in Br2s, right? How many can I make? 1.5. Beautiful. So, Carson, I would balance this as 1, 3/2. Yep. Now, if you would prefer You could balance this as 2, 3, 2. If fractions just scare the daylights out of you, right? You can do that. But one of the reasons we'll do this, hey, when we did that practice problem at first, what would be the delta G for a BR2? Because it's just a pure state, the way it comes, it would be 0. And so I wouldn't care about the 3/2 because it's 3/2 times 0, which is still just 0. And so that's where a lot of the fractions come in useful, is this one is going to matter. It's not going to be 0. But you're just multiplying by 1 because of the fraction speed. Does it make any sense? So it's okay to multiply these if you need to get rid of the fractions. All right, everybody happy so far? Good. Okay, yeah, steps. Okay, here's a step-by-step. All right, you like having a step-by-step, here's one to put on your cheat sheet. I recommend you just practice these. If you'll practice 72 of these, you will no longer need it on your cheat sheet. Okay? Well, I mean, well, look, the same thing goes for your, that didn't use or linear algebra you in polygon. What math class did you ever do? If you use, you'll just do 72 of those problems. It'll get clear. Right? So look, that's the way math problems are, and these are math problems. 72 came from, it's just a number of today, I don't know. So, okay, well, 73 will help you, I don't know, you may peak after that. 73 might be, I don't know, right on. Yeah, there you go. All right, well, we're going to talk about those two reactions I had on the previous screen, those two right there. So, using words, tell me what's going on right here. That's what's happening right here. What did? Copper is losing electrons, we call that oxidation, right? Because it's going from a 0 state to a +2. All right? Here what's happening right here. H is silver.
Silver is the.
Gaining electrons are being reduced. Okay? Now, let's think about it. Physical properties. What I am saying is happening. That's supposed to be a copper wire, right? And this is a solution containing silver ions. Okay? Dissolved silver. Now you put that copper wire in the dissolved silver. What happens? Well, no, wait a minute. Why did my solution turn blue? Because the first thing you said is that the copper was oxidizing to copper ions. Will make you a solution of blue color. Right? So that's where the blue is coming from. This copper wire is actually oxidizing and becoming dissolved copper ions. While the silver ions that are in solution are becoming not dissolved. They're becoming actually metallic silver plated onto the wire or onto the bottom. Some of them plated the bottom. But they're actually becoming metallic silver. And this is actually how you plate things, right? Y'all heard of gold plating? What is gold plating? What does it mean? Gary, have you ever had any jewelry that was gold plated? Yeah, because it's a very, very thin layer of gold over something else, usually copper, right? But something else there. So if it were pure gold, you're right, because if the layer of gold flakes off, it's gold under the gold, right? But if you just plate, now, what does it mean for it to be plated? What does that mean? I know y'all use it. I know y'all heard the term, right? Gold plated. What's in your head when you use that term? Have you ever said that? You ever used that word? You've never used that word?
Talking about your real.
You do talk about jewelry, or you don't talk about jewelry, okay. You ever talk about something being gold plated as like? No. Yeah. It is actually gold, right? But what the gold plated jewelry has, it is something, not gold. Like this is some like wire, making a bracelet or something like that, right? This might be copper or whatever else, whatever the base underlying metal is, right? And then it's got a few atoms of gold along the surface. Okay? So what you see is gold because it's coating the surface. But underneath it is not. Most of the bulk is something else. Because it's just gold plated. That's what's happening here. We're going to gold plate that copper wire, or silver. We're going to silver plate that copper wire. Okay? So that's what we're talking about. Interesting, which y'all don't have context for. A lot of this stuff is written, I think it's old, and thinking that you have context for things that maybe y'all don't think. Well, this is a typical, okay, hold on, before I do this. Let's think about electrons. What's happening electrons-wise? Now, that you said that the copper was being oxidized. In that half reaction, what's happening to the electrons? Are they on the reactant side or on the product side? Yeah, they're on the product side, on the right. Does that make sense? So they were on the copper and they're falling off. Okay? And where are the electrons going? Onto the silver. So electrons must be then, we're just going to say, flowing. Electrons are flowing from the copper to the silver. Does that make sense? Okay, cool. Now, so this is the typical way we're going to, yes?
So if we make that equation, we're running up the half.
Mhm.
The electrons on the product side is oxidation.
True.
I remember doing that last year.
You got it. Okay, so this idea that, now we did that all in a single test tube. We shoved that copper wire down in the silver solution and let electrons flow from the copper to the silver, right? What if we took those two things, those two half reactions, and we separate into two different test tubes or beakers or whatever's, right? And then, so over here, we've got the copper oxidizing, right? And over here, we've got the silver being reduced. But the electrons still want to flow from the oxidizing copper to the reducing silver, right? Does that make sense? That's what all about. You see it? You have this potential on this side. The electrons want to fall off of that copper. And the electrons want to go get on the silver. I know I'm personifying electrons as if they have wants and desires, but stay with me, right? The electrons had rather go live with the silver than stay with the copper, right? Well, that potential, that voltage in between the two, we stick a wire in between them, there's a voltage, they'll just flow through that copper wire or whatever wire, right? To get from one side of this to the other. Does that make sense? So that's how you make a battery. You put up a chemical situation where the electrons had rather leave this relationship and get in this new relationship over here. That's potential. That's voltage. Okay? Does that make sense? All right, well, this diagram you're going to see over and over again for these two lectures. Because this is a typical setup for a redox. We will put one half reaction on one side and the other half reaction on the other side. And we're gonna play with all these pieces in between, okay? So get used to this diagram. It's coming over and over again. How many times have you seen this diagram, Allison? Oh, you know? I'm gonna call this a galvanic cell or voltaic cell, but the idea is that it sets up a spontaneous negative delta G reaction that is going to move electrons from one side, one electrode, we're going to call it the anode, where oxidation is happening, to another electrode, the cathode, where reduction is happening. Okay? Then, once we have it set up and flowing, you can actually attach a voltmeter, just like you would use, people don't have it. Any of you ever used a voltmeter before? You have one, yay. They're losing context. That is interesting. I think this course needs a redesign because the students don't have the context. They've never used a voltmeter. They don't know.
I've seen.
Okay. Where have you seen one used? Oh, there's some YouTube channels with voltmeters on them. Some of them involve smoke too. You see some of those? Oh, there's a guy with I think it's a Czech accent that like he does some relatively stupid things sometimes.
The electric guitar.
No, I haven't seen that one. That one's
It
great.
basically just charges up the wires on the guitar and just go.
Hey, okay.
I think he's the person who's actually an electric engineer, so he knows what's safe. and what's not safe.
Yeah, but it doesn't look like it. Okay. Oh, no.
I use this is bad.
Okay, all right, nice. I remember that in Egypt with the water heaters, the gas water heaters, like and they're usually in the shower with you.
Electro?
Yeah. So just like gas flame, heating water before it goes out of the shower, yeah. Interesting. Don't slip, right? Okay, so, but you can actually hook up a meter and see how much voltage there is between one set and another. Okay, if you go to AutoZone because your car will not start, and they check your battery and it says, do you have a dead cell? Cells are these compartments of half reactions. If you have a dead cell, something has happened. You got a short or something, and it's not working because of that. So let's see, what else can we pull? Notice that concentration is going to become important, right? And that we're going to have, sometimes we'll have spectator ions, like this nitrate on both sides. So the nitrate on this side becomes nitrate on the, no wait, that doesn't really matter, does it? That's why that's there, is just so that you can have the chemicals dissolved in the first place and you won't have to care about nitrogen. Okay, it's called spectator ion, also changed in one term. So what we'll do is we'll take this copper metal, 0 oxidation state, right? This is just copper metal. We'll dip it in this solution that has copper 2+ ions. I had to look because copper has different oxidation state. We have 2+ right here. So now, so you can see that you can have a reaction from the 0 to the 2+, right? Where the electrons go. Both this wire came up here. You get this silver dipped into a silver 1+ ion solution. The electrons can get on these silver 1+, producing them. Okay? There's our half reaction for silver. guess I already did the half reaction for copper, right there. And then you notice that there's another piece in here called a salt bridge. If you have any physics, you know that a circuit needs a complete circuit, right? Think of that as what the salt bridge is, it's completing the circuit. Also, what it's doing is it's providing a flow for counter ions, like as you are pulling, as you're pushing those copper ions out, there are 2+ ions in that you're putting in solution. You need negative ions to go in solution with them so that your solution itself is not building up charge. Same thing on the other side, you need a sink for the nitrate ions to go getting it. That's your salt bridge. And that's all it's doing is it's maintaining electrical neutrality. Okay? And it's a flow of ions in the salt bridge. We'll usually draw it in. It can be done with a string, it can be done with a lot of times we'll do it with a tube, and we'll actually pack the tube full of salt. And so that ion bridge is what completes the circuit. Okay, good so far, y'all? Yes? All right, now let me, I want to see what it says. Oh, it's way up here more. I'm gonna move it. I wanted you to see how this is normally written. This is called cell notation, right? So what you're normally going to see in a textbook, they're not going to draw the cell every time, or especially when you're in upper level inclines and stuff like that, they won't draw the cell every time. They'll just use what I'm doing is a solid vertical line to separate what we call phases and states. Okay, so you see that the solid copper is in a different phase than the aqueous copper. Then I'm going to put in a salt bridge. That's what we call cell notation for one of these. So be able to do that as well. But basically what you're doing is you're saying, here's my oxidation reaction. This side, separated by the salt bridge, and my reduction side over here, okay? And you just show, that's just kind of a way to show that. Make sense? You can do that? Maybe? All right, cool. Let me think. I don't think I got as far as I would have liked. Start the homeworks, turn in what you can. Let me see what I put up on the homeworks first.
What was that one?
The salt bridge. Actually, separation of the cell. All right, so you can do 1 and 2, no problems, right? Oh, okay. All right. See this? So let's do this. Now we'll work this up. Go ahead and turn in a version name. I'm gonna use the same questions for the next homework. Do the parts that you can do right now. So Alexis, when you're looking at this, right? See that part A, B, C, okay, balance it, redox, you do that. What's reduced? You can do that. What's oxidized? You can do that. Okay, but let's see, how many electrons are transferred? Oh, you know what? We had 3, yeah, so we could do that. That make sense? But now there's another piece. What's the standard potential? You can go ahead and do that. You can read about how to do that, but we'll come back to that on Wednesday. Okay? But go ahead and turn in with everything that you can on this first, so that you know what the hell I'm talking about on Wednesday. All right? Oh, what do we have left? We've got, now that today is over, we have 4 more meetings, is that correct? 4 more meetings. One of those is an exam day, okay? That means 3 remain. So y'all need to be thinking about that and talk to me on Wednesday about when do we want that exam to be? Do we want it to be on that last Monday, or do we want that last Monday to be a review day for that cumulative final? Y'all think about that. Be ready to discuss that on Wednesday, okay?